So welcome back, everyone. This topic, convolutional neural net, we are going to start, and it represents a departure from the basics. We are done with the basics. We have built the foundation for neural networks. We know what loss functions are. We know what activation functions are. We know what linear transformations are. We know why, using all of these together, you can, with the help of gradient descent on the loss function, you can achieve a universal approximator behavior of with a neural network, which is a massive statement to say that a neural network is a universal approximator of any functions. We have done labs on that. We did something much more specific to neural networks, namely backpropagation in a multi-layer neural network. So our foundations are laid. The second half of this course, or the remaining sessions of the course, we will now get into a much more functional perspective. You will see that there will be almost no math. The math is over, and some of you are cheering, I see. Right? So it will get much more practical, much more real. The concepts will get interesting, but it won't be that mathematical. We'll be using all the math we have learned, and we'll move forward. In particular, we'll be going through quite a few very interesting neural architectures. The world of neural networks, or game with neural networks, it usually comprises of two things. Dreaming up wonderful architectures after a lot of research. And as you conjure up these neural architectures, each of the architecture has special strengths and weaknesses, and they make special assumptions. And along with that, the other magical element is loss function. You will see that most research papers are positing either a new neural architecture or some adaptation of an existing architecture, but for making modifications to it, or they're often modifying the loss function associated with the neural. Right? So these are the two great areas of research, often. So as we move forward, we will do convolutional neural networks, recurrent neural networks and LSTMs. We'll do attention networks. Are we together? Transformers, diffusion models, energy models, flow models, normalized flow models. So we will, in quick succession, do as many neural architectures as possible: autoencoders, variational autoencoders, GANs, generative adversarial networks. And you will notice that very quickly we are entering into the territory of generative AI thereafter, which at this moment is a dominant topic. Is that clear? Now, if you go to the course portal, you will notice that I have put a summary of what neural networks are, what convolutional neural networks are. At the same time, I have put this. You will see some quite interesting thing. One resource in particular that we'll use in the class today is the CNN explainer. This we will use to explain the concepts of today. I have also mentioned that of the easiest of the 5 textbooks that I've recommended, and I said, pick the one that suits your needs. This one, Dive into Deep Learning, could be the quickest way for you to review the sort of things that we are going to talk about today. Now, you'll realize that the ideas are beautiful, but they are simple with CNN. Then, these are articles or things that I would advise you to pay attention to. Chris Ola's must read on feature visualization. Highly encourage you. What is the machine seeing? See, when we see a horse, right, or we see a landscape, a beautiful landscape, or a house, or a child, what is it that the machine is seeing? It would be really worth understanding or interpreting or looking through the eyes of the neural network. So that article you'll find useful. Inception was one of the neural architectures, CNN architectures, convolutional neural architectures, that had a huge number of layers. Right. And is amongst the state-of-the-art convolutional neural networks today. So this is the article. This is a Google page on on inceptionism that they call it, going deeper in neural networks. Interesting play on words, but basically it's one of the deeper, or rather fairly big, convolutional neural networks. And this is a collection of CNN architecture. So convolutional neural networks itself has many variants. So if you look at it, go down, you will see a lot of, so exception is the one that we just talked about, ResNet, Inception, Inception V3, GoogleNet, VGG, AlexNet, LeNet. You may think, oh, well, just a catalog of networks. But for the people who are in this field in deep learning, they have fond memories, because each of these networks that you see here, they represent a massive milestone in the field. Starting with LeNet, which did handwriting recognition, and it was already doing it, I believe, in 1998 or something like that. Right? It's the simplest convolutional neural net that you can create. AlexNet is the one that shook the world when people realized in 2012, was it 2012 or 2014? I think 2012, that deep neural networks or deep learning was for real. It completely beat the state of the art by a huge margin, and was taken very seriously. VGGNet, ResNet came right after that. Right? So these are classics. These are great architectures. Do we still use them today? Are we forgotten? We use them very much today. Right? So these are architectures, and depends upon how deep you want to go down the rabbit hole. But if you are going to be in this field, what you should do is budget time out. One advice that I give people is, see, you have a whole week to learn convolutional neural. I'll introduce you to convolutional neural. What you can do after that is, all the resources that I've put here, do invest time going through them. Right? In particular, your time would not be wasted at all if you take even a handful of these core architectures and you read those research papers. After the explanation, you'll find them relatively easy to read. And while I may not get time to do this in this introductory course, you can really deepen your knowledge by reading those papers. No. Now it gets a lot easier. We get into a very applied area, and you will see that what I'm going to talk about are very simple ideas.
You said like how the vision is seeing object, right? So can I compare with the computer vision?
See, we'll come to that. I'll explain it. This is it. It's very simple. Computer vision is literally that, how the computer sees the world. Right? And the computer sees the world like this. CNN see the world like this. We'll see it in a moment. Yeah? So that's the theory I'm going to explain to you. Guys, today we'll have a slightly longer session. I will stretch 1 more hour at least. Is that okay?
Yeah.
I notice it's already 9 o'clock. How did it suddenly become 9 o'clock? I have no idea. So I will start a new page, and page color black. So I've suddenly changed to black, guys, because of people here, to prevent glare. Page color.
It's a lot more readable remote as well.
Okay, that's good. Nice. So I said no math, and then I'll start with math.
I mean, it's maybe a dumb question. Really, I mean, at least from my side, like those who understand what it means, but what I'm not able to understand is, will I apply these mathematics in the real
No,
implementation?
you'll not. But at the same time, it's a necessary thing to know, because it informs. When you get stuck, when your loss function, you see it's not happening. What happens is there are 2 ways people solve problems. Just hack, try. The other is, if you can reason through it, generally you have a much shorter path to a solution. And all that I taught you, hopefully, gives you the ability to reason your way out of problems in real life. Or if somebody says, what should I build? How should I build it? 2 ways. Just Google around. Has somebody done something? and start with that as a basis. Or alternatively, you can say, yeah, I'll survey what others have done, and I have a sense of judgment which is the better approach to pick and use as a starting point. Yeah. Because when you understand the foundations, it just helps you make better choices. Yeah. But generally, you'll realize that these architectures are done. Even what I'm going to explain, convolution, most of the time you'll download a convolutional architecture, just download and apply it to your problem. In fact, you'll see it in the, as we go into the lab part, you'll see that it is very simple. People have created, these models are not easy to train. Some of these inception, etc., they have been pre-trained to a very high degree of capability. And when you take these models and you apply to a problem, it feels practically magical. How in the world is it able to do that? So that part, how in the world is it able to do, is what I'm explaining. Because then you're using a tool that you understand. Right? So let's go with that. So I'll just take one last residual bit of mathematics. See, and you can close your eyes. I mean, you don't have to listen to this. I'll just throw it there for the sake of completeness. See, whenever you have a function, right? And let's say that you have a function like, well, this hardly looks like a function, but let me take some function fx. This is your x-axis. And you want to get a local view of it in a particular region, right? What you can do is you can sort of apply some sort of a windowing function, like a function which takes on value. Let us say, suppose I have a function like this, bell curve like function. All I need to do, and suppose I get the freedom to move the center around, right? So suppose I want to get a local view of the situation around here. What do I need to do? I can go slide my function to sit here. Are we together? And then if I multiply, let me just call it g of x. Now think about what happens when I multiply fx with g of x. Let's look at 3 points, A, B, C. Now look at the product of these two. Well, see, I'm being deliberately mathematically imprecise. The real equation is a little bit more complicated. It is g x minus tau d tau and so on and so forth, right? But ignore that. Let us just ignore that for a moment. Think about it this way. What is g of x here? Look at this point. This is the orange line. What is this value at a? 0. So you realize that this product function at that point would be 0. What about c? G of c is 0. So g takes non-zero values only in the vicinity of b, right? So what does that do? The reality, the product reality, if you look at this function, let me just call it the c of x, roughly speaking, you realize that it will give you a very localized view, of reality. I don't know if this thing will show up. No, it won't show up here. More, let's see, strong color.
Asvango, could
It
you
won't let
explain
me.
why g of c is 0 and g of a is 0 as well?
Because this function, if you look at this function, this is the orange function. What is the value of the orange function at c? Sorry. Look at the orange function.
If you extend the line to the left and to the right, yeah, that'll explain it.
Ah, okay, got it.
It is 0 at both of these places, right? 0, 0, 0, 0. And so if you multiply the function, the purple line with this orange line, the product will disappear everywhere, and you get a very local view only in this little window. Maybe this little window, you'll see only that little bit of purple line, basically. this part, this purple line, is the only thing you will see, more or less. Does that make sense, guys? Right? This is what you'll see as a product. Right? So what you say is that, and not only that, there's something else. If you integrate, I mean, you sum over all of that, it is like you're averaging the value, you're convoluting, you're averaging the value across this segment, multiplying it by this and so on and so forth. So the pronounced value will be somewhere around here. Think about it. Does this make sense? It's just picking up the value. So this is the only math I want you to remember, that convolution in a way is a way of looking through a window. Are we together? Looking through a window and saying, I'm going to look at only this much. That is convolution. Right? So long as your G function is a localizing function, it's a tunnel vision, right? It gives you tunnel vision. And wherever you place it, it will just look under that. One easy way, one easy intuition that I have of that you can carry is that, you know, if you have a magnifying, imagine that there's a newspaper and everything is written in very small fonts, right? So what will the magnifying glass do? Wherever you take the magnifying glass over the newspaper, you'll be able to read only that, right? Or those of you who have played with microfiche and all of this in the library, you see that, right? You have to scan it over the whole thing to be able to read. Am I making sense, guys? That is convolution. That's a convolution. The magnifying glass is in effect a convolution function, right? That's it. That's the only intuition you need to have. Now, what does it have to do with neural networks? Here it is. The intuition actually is very simple. Suppose I have a complicated picture here, and the picture has, like, you know, kids always draw, like when I was a kid, I somehow remember that in kindergarten, the moment they say make a landscape, I would make something like this. There would be birds flying, there would be a tree growing, and there would be a river flowing. Right? A lot is happening in this landscape. Does it remind you guys of your own drawings? Right? So now, suppose I ask this machine, go understand it. So let's pretend that we are the neural network. We have no idea what this is. Right? Now comes the concept of how can we train a neural network to identify things in it. So we could ask questions, is there a tree in the picture, and so forth. So one way to do that is you could use, for example, a deep standard feed-forward layers that we are familiar with, right? And when you use the feed-forward layer, what does it do? It will just, first of all, you flatten the whole image into pixel, one single vector. And then you feed it into a deep neural net, feed-forward layer, the ones that we have been doing. And then you ask as a classifier, was there a tree? Right? Was there a sunrise? And you'll get some accuracy. Am I making sense, guys? But when you flatten an image, when you flatten this, you're doing a very generic process. You're making it into an X vector, feeding it into a neural network, which will act as an approximator. And then you're saying, was there a tree? And it will give you some accuracy. Right?
So, quick question here, just to clarify.
Yeah.
So, say we flatten, let's say it's a 100 pixel by 100 pixel image. So, we get a vector that is 10,000, has a dimension of 10,000 by 1. Is that what it is?
That's exactly what you get.
Okay, thank you.
It will become a single vector. So 100 by 100 will become a single vector of 10K. Right? But as you realize that somehow it seems not the best way of looking at pictures. And here I'll introduce the word, an important point here, guys. See, neural networks, despite their enormous popularity, they are not always the best algorithms. When you're dealing with tabular data, even today, the state-of-the-art neural networks are barely able to compete against very old algorithms like random forest or ensemble methods, support vector machines. Right? They're not able to do as well against that. And the part of it is that there are many reasons, but one way to think about it is that when you can't make any assumptions about the external world, then neural network as a universal approximator goes so far. Other models which make much more, in some sense, stronger inductive bias, or they make some presumptions about the world, sometimes give you better results. They are better machinery to deal with. So if you write a SQL query, feed it into algorithm, you must be noticing that most people who do statistics or on data, like tabular data, they are not using a deep neural network most of the time. Though the situation may change, deep neural networks are sort of beginning to catch up there, but generally, traditional algorithms do much better, which is why all those textbooks are, even today, mostly with traditional algorithms. A lot of technology. For example, the scikit-learn library is not going anywhere. It is heavily utilized. So if I were to ask a question, where does a neural network shine? It's a question worth asking. Where is it that neural networks or these deep networks, they shine? And it is a question that very few people are asking these days, but I want you to know there is a theorem in, so see, our field of engineering is very practical. We build things. Engineers build bridges and then people go over them. Engineers create electricity and people then use electricity or the telephone or the planes or whatever it is. Engineers rarely contribute to the foundations of knowledge itself, to epistemology, to the theory of knowledge itself. What is knowledge and what are the limits of knowledge? There is one contribution that our field has made to the foundations of knowledge itself. That goes with it must have a very serious name, right? Anybody can guess what that name is? It actually goes by a very frivolous name. Actually, it is theorems, no free lunch theorems. It's a group of theorems that are pretty much saying the same thing. Now, no free lunch actually comes from an Irish heritage. At one time, the Irish are known to, or the stereotype about them is, they have a strong love of their pubs. Right? So at one time, one pub decided to offer free drinks. Right? Oh, no, sorry, a free lunch, because they realized that, and as you see, even in US, if you go to a pub, the bigger part of your bill comes from what?
Drinks.
The drinks. Right? Another argument why one should never drink. So then they announced that food is free, lunch is free, lunch is on the shop. So then, obviously, people would come for lunch. Most of them would get tempted by, after all, they're Irish, so they would love the drinks, and the shop had a pretty good profit. Then they started noticing that there were some free riders who would just come for the lunch. So then they put a rule: no free lunch. You have to buy drinks to get the lunch. So therefore, the term "no free lunch," which has become part of common usage, it turns out that one of the significant contributions that machine learning made, perhaps the only one to the foundations of human knowledge, is the no free lunch theorems. It says something very deep. It says that the world is filled with many algorithms, machine learning, from the very simple, let's say, a decision tree or a linear regression or logistic regression, very basic stuff, all the way to some pick your thing, some really ginormous transformer. Now, what the no free lunch theorem says is something quite counterintuitive. It says no one algorithm on average will outperform any other algorithm across all the data sets in the world. Right? So every algorithm has a place to shine. It has a place under the sun where it will shine. And there are places where it will not do well. Does that make sense, guys? Right. So it turns out that when you have tabular data and things like that, neural networks, that's not the place they shine. It's a thing that not many people seem to know. They think that, oh, these generative models can do just about everything. Actually, many areas they're very weak, and it is not something you can ever remedy because of the no free lunch theory. It will, and the reason for that is every model makes implicitly a hypothesis about the external world, right? So linear regression, for example, says the relationship between input and response is linear. It's a very simple assumption. Quite often it's not true. So there it does poorly. But quite often it's also a good approximation. So it does quite well. You see that, right? So it's the data that rules, that tells, because behind data, there's some generative force, and that generative force determines. You have to approximate that generative force. Different algorithms are good or bad or weak at mimicking the generative force based on the underlying assumptions they make. So remember that. But there is one area, the areas where neural networks shine, they all have one common characteristic. Can you guess what that characteristic is? Anyone?
Lots of data.
Lots of data is one. When you have lots of data, you can take a very complicated neural network. Yes, that's a good answer. And they somehow seem very resilient to overfitting. So even with a feed-forward network, because you don't make an assumption about, it's a paradoxical situation. You can imagine that the reality is very complex. Imagine, if you think in terms of polynomials, it's a very high degree polynomial, 100-degree polynomial. Now, the moment you think like that, you notice that lesser algorithms, they begin to stumble. It will be very hard to fit it to that and so on and so forth. But neural networks have a very interesting ability. You can throw it at the data, and even if the reality is actually third degree, you can still get away with a very complex neural network, and it manages to simplify itself internally as you feed it more and more data. So data acts as a regularizer, and counterintuitively, neural networks' internal structure also acts as a regularizer for reasons we don't fully understand. It finds simplifying paths through the analysis, and they'll still come back with a third degree, what is effectively a third degree approximation rather than a 100-degree approximation of the function. Right? So that is one aspect of it. So people say that it's worth mentioning that people often represent it by saying that if you look at the complexity and the performance of the model, let's say performance in the AI sense, AI performance, that is model performance. For example, accuracy. Let's take for classification accuracy as accuracy, precision, recall, pick your thing, or regression, mean squared error, whatever you want to take, etc., etc. Take it. What you notice is that classical algorithms, they all flatten out. After a certain time, throwing more data doesn't get you much. Are we together? So you have an asymptote or plateau, in common terms, plateau. So, but the neural networks have this quality that we observe, that their accuracy actually starts out lower, but what we are seeing is this. It just keeps getting better and better and better with more and more data. Right? This is one reason why we favor deep learning algos. That's one reason, one way to look.
What is the yellow curve again?
A classical algorithm. So let me name them. A typical classical machine learning algorithms. And the blue one is the deep learning algorithms. Right? Deep learning networks, they tend to just go on and on and on. And actually, they underperform with small data sets. But after a little while, they catch on and they begin to, there's an inflection point after which there's no stopping them. They keep getting better and better. Right? So that is one. Then the question to ask is, but how is it that if that were true for a lot of tabular data situations, they actually can barely keep up with traditional algorithms? What are the situations where the blue line moves? And the answer to that is quite interesting. It turns out that neural network, the way you architect neural networks, it is far easier to bake in things that mirror real life, real world. It's much easier to bake in things that mirror the real world. Or the way to say it is that you can create neural architectures that have strong inductive bias. You bake it in. Right? So, for example, and the convolutional neural net is a classic example. So let's go back to our example of a picture. There are two hills, sun rays, etc., etc. Now, what are the things that we can be sure of? See, the sun would still be the sun peeping through the hills, or the sun would still be the sun if I move it up or down a little bit, isn't it? For example, if the sun or this picture, there was a cloud here, there's a cloud here, and the sun was peeping out from this instead, it would still be the sun, it just has moved location, isn't it? Would it not be nice if we had a neural architecture that would keep the sun as the sun? Right? But think about it, when you flatten it out, now sun values, they have completely gone haywire. Right? You don't know where they have gone. They have moved. Sun's pixel values have moved somewhere else. But in real life, a sun is a sun, a bird is a bird. And you could move the bird from here to here. It would still be a bird. Right? The hill would be a hill and a tree would be a tree. So you need to think of a neural architecture that gives you, the word that you use is translation equivariance. Right? Means if I move the tree from here to here, right? So for example, if I move the tree from this to here, then somehow the neural network should have a representation in which the representation also has just moved a little bit, but tree has remained a tree. Does that make sense? The cat was sitting upon the tree and now it has climbed down the tree. Cat is still the cat. Am I making sense? This is how real life behaves, right? So that is, let me start putting those terms there. Translation equivariance. Oh, quite a mouthful. What it just means that if I move a thing, then its representation should equivalently move. Right? Or another way to think about it, if it helps you guys, that see, suppose your shadow is projected on a wall. Right? Imagine there's a fire, and in front of the Plato's Plato used to give this example quite a lot in his philosophical discourses. That imagine there's cavemen. There's a fire. Cavemen are doing things, and their shadows are being projected on the walls of the cave. So here's a caveman, and he goes and moves here. What happens to the shadow? Shadow is a representation of the caveman, and the shadow equivariantly moves. Right? That is translation equivariance. Do you see that? So that is something you see in the real world. Am I right, guys? Right. Then you also have something that things have locality, local structure. Right? Local. So in other words, one pixel, when you're looking at the sun or the bird in the sky, the pixels are all closely related, isn't it? For example, the eyes of the bird, all the pixels, they add meaning to the eye. They have a local structure. Does that make sense? So locality is something. Now think about it. In a traditional algorithm, those things are hard to bring up. So you call this locality. You see locality in imposing meaning and structure onto the into what you're seeing. The other thing that you see is hierarchical structure. Right? So for example, you have the iris, part of the eye. Eye is part of the face. Face is part of the bird. Do you see how structure is hierarchical? Isn't it? This is what we see in real world. Are we making sense? And the whole structure is stationary. Like you move it somewhere else, it will still be the same thing. Cat here and a cat there. The sum total, this whole big thing, is still that. It isn't that you move it from here to here and now the tail is growing out of the nose. It's not like that, right? The cat doesn't change. There's certain stationarity to it. Right? These are the things that you observe in the real world.
Asif, can you explain what the hierarchical structure means? Is it
What the hierarchical structure means.
is it specific to an object?
Yes, the real world objects, when you look at a scene, when the human eye sees, or imagine a photograph, you notice there's hierarchical structure. You're looking at a bird, let's take another example. You're looking at your car. There's the headlights on the grill, adjacent to the grill, on the front of the car, together making the car on the street, on the road, which is part of the street, which has houses there. Do you see how the scene is hierarchical in nature? Right? So these are, and there are a few more such conditions. There's a stationarity condition and so on and so forth. But these are things about real life that we see. You would like to have a neural architecture that looks at the world in a similar way, looks at data in a similar way. If the data shows hierarchical structure, hierarchical representation, it should also be able to reconstruct a hierarchical representation. If you have translation equivariance, that representation also should exhibit translation equivariance somehow, right? And these are good things, and local structure, locality, and so forth. These are, you need, in other words, what you say is that it should preferentially build up from the local to the global. Are we together? And we see that. People have done sections of the cat's brain to see how the image from the retina is effectively being processed in the brain. And they found that for each part of the image, you can pinpoint areas of the brain where the receptive field is. Right? So inspired by that came this architecture. So think about it this way. When we say that this part of the brain here is responding to this part of the image, can you guys relate that idea to, oh goodness, this thing, this abstract thing that I said? It is as though that part of the brain has a tunnel vision and it sees only this part of the outside world, isn't it? It's convoluting and seeing this part of the outside world. Does that make sense? Of the image that's coming, information that's coming from the eyes and entering the brain. And if you think of the brain in the background as an analogy, as a screen onto which this image is being projected, a part of the brain has a receptor field limited to one region only. Is that convolution? Isn't it? And that is the inspiration for a beautiful architecture and one of the most dominant and long-standing and resilient architectures in neural networks, and a great place to start our journey into neural architectures. We'll encounter a lot of beautiful architectures. This one in particular has stood the test of time. Is the reason why your letters today arrive in such short time, and you don't have dead letter situations. In other words, letters don't get lost. They recognize your handwriting. They do many things, medical diagnosis, manufacturing defects. You send, these days you send probes and vehicles to dangerous areas. Everywhere, this CNN has been the workhorse for decades, and people didn't know that actually. The LeanNet is now more than 2 decades old. LeanNet is, I'll take questions, guys. It's been, but its real movement came when it truly got into people's imagination was in 2012 with the coming of AlexNet, beating the benchmark, which is the MNIST. There was a data set, handwriting data set called MNIST. NIST, you know, National Institute of Standards and Technology, they had created a benchmark that for decades people were competing, and it was to recognize the handwriting, digits 0 to 9 correctly, for example. And they were getting pretty high error rates. If I am right, and don't take my word for it, the state of the art when the deep neural nets took over was either 23% error or 26% error, I forget which one. And then this convolutional neural architecture came. Literally, it made a difference. It brought it down to something like 16% in the get-go error rate. After that, subsequently, it brought it down even further. Today, the error rate is like the accuracy is 99.9 something, right? And the ones that are considered mistakes, no human being can tell what it is. In fact, it's beating human beings absolutely hands down, right? So we will look at it. So look at that. Let's see what it is. I'll take a number. I write 4 like this. Then I write it like this. Then some days when I'm really in a mood, I'll write it like this. Some days I'll write like this. Do you see that even when I write 4, there are so many variants? Somebody may write it like this. Everybody has a different style of writing. A 4. Are we together? Making sense? So then, how in the world can you distinguish this from, for example, do you notice that this begins to look a little bit like 9? I can write my 9 like this. Now, is it a 9 or a 4? Human beings can spot it. Creating algorithms that can spot it is a bit hard. And the key insight that convolutional neural nets do is that if you really think about it on a piece of paper, think about it this way. Whether a 4 is here or a here, it's still a 4, isn't it? So whatever neural architecture you create, having translation equivariance is a good thing in that. You want local structures. Look at local structures and build from it. And things build up, right, for the cat's eye and so forth. So it beat in 2012 and subsequently in 2014. After that, there was no doubt. It was the moment, just like ChatGPT was the moment in public's imagination for NLP, chatbots, for computer vision. The moment was between 2012 and 2014. Right? A lot of remarkable breakthroughs came, and we are discovering, or we are discussing
What was
about
the example? What was the example? Check put my check on ATM. It's reading the number. Was the first thing, or what was?
the first thing was just postal service and writing
was
information.
reading the business.
Yeah.
And that's the MNIST data set that you're talking about.
Yeah, this is the MNIST data set that I'm talking about. MNIST.
So this is the one that gave 99% accuracy. Is that what
Yeah, nowadays it's like it is considered so easy for the modern neural networks that you don't even assign it as a homework.
The hello world.
That's it.
The hello world.
It's the hello world. It's not even worthy of being a hello world. So people have replaced it with a fashion MNIST. Fashion MNIST is basically lots of dresses, right? And now you can imagine figuring out a dress is much harder than digits. So that is the new hello world, fashion MNIST. So how does this architecture work?
So is the deep learning algorithm can be used only in the CNN model, or it can be used on any common model?
I don't understand the
The
question.
CNN, all the convoluted neural network, I think they are using deep learning algorithm. By deep, is it the classical and deep learning? They're the two.
No, you are totally, this entire course is about neural networks.
Okay,
So CNN
which
is a
algorithm?
neural network architecture, neural network only, and you'll see it in a moment.
Okay.
Right, so
But it's not a deep learning network, right?
Yeah.
deep learning just means that it has many layers, and certainly CNNs have many layers, and therefore it's a deep neural network. See, here's the thing, guys. First, right, people created the paper of Jeffrey Hinton. Anyway, this is a bit of an aside. In 2006, he wrote the paper, which was basically the paper had restricted Boltzmann machines, this and that, but it heralded the rise of representation learning, which is what I'm going to teach. CNN is a classic example of representation learning, right? Then came 2012, 2014, when CNNs really began to take off. Beautiful illustration of representation learning. And then it used to be called deep neural networks. And then somebody had a master stroke of marketing genius, right? And they decided, oh, people's imagination, let's call it deep learning. Right? Sounds deep, isn't it? And so the word deep learning has sort of taken over the field. I still prefer deep neural networks. Right? So it's just a buzzword. Don't get too carried away about a buzzword. Right? When I first heard deep learning, it almost sounds like philosophy. But
also this is different from transformer architecture, right? Which
no,
was
nothing
published.
to do with transformer. Nothing to do with transformer.
Architecture.
Mahesh, this has nothing to do with transformers.
So that's what I'm saying. So this is a very different architecture from the transformer architecture.
Very
Right?
different. Very different. As I said at the beginning today, we are now going to visit some of the great classic architectures in deep neural networks. We already know one implicitly, the feed-forward network, the multi-layer perceptron, and whatever you call it. Now we are going into the new architecture called convolutional neural network, CNN. We will come to transformer also later in the course. It's just one of the many architectures we'll do.
So his question was more on that CNN can be used for any problem, right? Or something like that. That's what he was trying to ask.
Who was asking?
When he was talking.
No, I was thinking like the deep learning algorithm, you differentiate two algorithms, a classical machine learning algorithm and deep learning. So when someone can decide which one to go is only for the CNN model, by default they go with the deep learning algorithm.
No. So the wording itself is wrong, right? CNN is a neural network.
Yeah.
So first of all, never use the word deep learning.
Okay.
It's just bad vocabulary. It's marketing, right? Neural network. CNN is a neural network. All right. So you don't say for CNN do we use a neural network. CNN itself is a neural network.
No, I mean CNN deep learning algorithm. There are two algorithms.
No, I'm saying there are neural networks and then there are other algorithms. Right? CNN is a class of is a type of neural architecture. See, guys, using neural networks can be used. So neural networks, right, are these nodes. Right? They are made up of neurons, right? We do remember the neurons. What do they contain? They contain a Z and an activation of Z. So far, so good, right? Now, by wiring these neurons, by differently wiring the neurons, we can create many elegant neural architectures. Just like, if you have bricks, you can make all sorts of buildings. Right? You can make a castle, you can make a train station, you can make a library. Each of these is a different architecture. Are you following me?
Yeah.
Right? This is it. Of the different architectures that you'll create, we are at this moment starting with CNN. It's one of them. Now, is it making more sense?
Yeah.
Okay. So CNN
Yeah.
is just neural you can create by wiring the neurons.
So can I have a quick question? So it might be that I joined kind of late out for these sessions.
Yes.
In the sense, like, what is the difference between a fast forward? Because you said that you've already gone over the fast forward neural networks in the previous classes. So can you can you provide a quick summary of the differences between the fast forward and the convolutional, if it's possible?
See, let me first explain what CNN is, and let's see if you can spot the difference. Would that be fair?
I have no idea about what is fast forward.
Okay, fast forward network is just layers into which you put the neurons. The feed forward, not fast forward, feed forward. And every neuron is connected to every other neuron. It's a very primitive structure, right? It's a very basic structure. This is a feed forward neural. Do you see that? That suppose I have A and it is connecting to A prime, B prime, C prime, D prime, E prime. So how many interconnects can we have here? 5 cross 5, right? 5 neurons connected to 5 neurons in the second layer. So there'll be 25 interconnects. So these are also called dense networks or feed forward. Why are they feed forward? Because the input that comes here, this one feeds it forward to the next layer, to the next layer, and the next layer. So these are called dense networks or feed forward networks. Are we together? Right. Now, keep this in mind. Now, what I'm going to explain is radically different from that. Priya, does that give you some basic idea?
Got it.
All right. So now let's finally come to this. See, let me refresh. What is it that I've been saying? I've been saying that we need an architecture where these things are inductive biases, translation equivariance, local structure, hierarchical structure, locality, hierarchical structure. There are a couple of more, stationarity, etc. I won't go into that. There are actually 6 conditions. But next time when I reiterate it, go deeper into CNN, I'll go into that. How do these things get encoded? What you do is we bring in the idea right from the way the brain processes images. What we do is this little window, remember, a small receptive field. What you do is you take a 3 by 3. I'll take an example, 3 by 3. By the way, it is any odd number cross odd number will do traditionally. You call this a filter. A filter. Are we together? Or think of it as a mask or window. Window. Then what you do, this is like this. Imagine that this is your little window. So as you look at the whole scene, if you couldn't see the scene except what is projected onto this window from the scene, whatever this window captures from the whole scene, that patch, that little patch is the only thing you want to see. Are we together? So suppose I get a big scene with lot happening here. Lots happening here. What you do is you place your window at the top corner and you convolute. Convolute means it has a way, it is looking for something. It may be looking for example, an edge. So I'll give you an example. See, so for that, let me take an example. Suppose you have a big fat, let me take a big fat 4. And imagine this is huge in size. And you do this game. You take this 3 by 3. Let's say that I put a value just because I feel like it. You put 0 or maybe -1 while we are at it. minus 1, minus 1, minus 1, minus 1, minus 1. Something like this. Why? Well, because you'll see why. So tell me what happens to this the moment you come across an edge. The moment you come across an edge, what will it do? So let me fatten this thing up. This 4, the pillar of the 4, I'll just fatten it up. Right? This area. Fatten it up here. Now think what happens. When this thing is outside, what is the value of the, if I multiply every underlying pixel, the pixel value for black is 0. So just imagine that is 0. And at this moment, by the way, imagine that this is all grayscale, 1 or 0, right? So the shape of the 4 is white, 1 and under. So this value will evaluate to 0. What happens inside? In there, in this situation, what does it evaluate to? Inside, the value is 1, the background value is 1, but when you multiply it with that and you sum up all the numbers, so what will happen? 8 minus 8. You see, all the minuses, minus 1 times 1 is minus 1. They will all accumulate, and what will be the sum that you will get? 0. So outside 0, inside 0. Right? That reminds me of a story in the Indian mythology. Apparently, a god, Shiva, gave a blessing to a troublesome guy that you can't die. Well, now this guy went about doing a lot of mischief. So then the god felt, okay, we need to modify it. So he put a little modification. You can't be killed inside and you can't be killed outside a house, leaving a loophole. So where was that person killed? Yeah, in the veranda, in the portico. And so this is that sort of a little bit of that blessing. Look at this filter. Where will it take value? Inside is 0, outside is 0. But what happens when it is on the edge? In the edge, you realize that this guy will shine. Do you see that? Right? It will not acquire the value 0. It will have a positive value. The sum of all the multiplications or the conjugate will lead to a positive value. Do you see this, guys? Yeah. And so what it will detect is the edge of this. It will end up, would you agree that it is going to detect the edge? And so you just found a little window, a filter that detects edges, right? Likewise, you could have a detector only for the horizontal part of it, a filter that can detect minus 1, minus 1, minus 1. Suppose I give it 1, 1, 1, minus 1, minus 1, minus 1. What will this detect? You can convince yourself that it will detect horizontal lines, right? Horizontal lines. Likewise, you can have a detector for vertical lines, and you can create a detector for diagonals, and so on and so forth.
Because the brighter image is going to be 1, light and the dark is 0.
Yeah.
Minus 1 comes. How the minus
1?
No.
No. See, the picture has a 0 and 1, right? But I'm saying your filter is literally made up of this grid of numbers. This is your filter. And you are putting that filter on top of the image. And you are literally taking the product. See, in Photoshop, you do that, right? You put a mask, and then it says, add, subtract, product. What do you do?
Oh.
Literally that. Right?
So adjusting that.
Yes.
Mask.
The mask is fixed. You take this mask, which is an edge detector, This is the horizontal detector. This is the vertical detector. So now you have a library of masks. And so you could go over the picture and detect all these things. Are we together?
I think it'd be easier to explain in the fact for that image, right? You not show the ones in the pink area.
Yes,
So
you could do that. Just see, guys, I am assuming that that is there. Let me repeat it. This inside is all 1. Outside is all 0. Right? Everywhere you put the filter, you multiply the filter value with the background value. To do so is convolution. Remember, that is what we did here. No? This was the concept of convolution. You see it? Multiply a function with a filter, with a convolution. So this is your convolution filter. Am I making sense, guys, or are you still confused? Anybody who needs more explanation?
So the edge becomes 1, is that what you're saying?
Yeah. The product, you will notice that only the edge values will remain. When you apply this filter on the image, what it does is it just pulls this out.
So that's for the edge filter.
For the edge filter, right? The horizontal filter will just pull the horizontal line. The vertical filter will only see the vertical line. Are we making sense, guys? Right? So each filter is a detector of a separate feature, very low-level primitive feature. Bhavan.
The number 8 in that grid, where is that function?
Because, I have 9. I judiciously pick 8 because the other ones, they're 8 minus 1s. So you can pick anything you want, but 8 is a good number to take. You'll see.
I mean, yeah, so I was getting confused about how that 8 is playing a role in detecting.
Yeah, so let's count how many box cells are there in this grid. 9. If the center one I don't want to put a negative number, I put -1 everywhere. What would be a good number to place here? Very obvious number to place here.
1 maybe, +1.
You want to place +1? No, it won't be. If you place, so let's say that you place +1 here. Now think about what happened with the edge. Will the edge stand out? No. But if you make it +8, it will stand out, isn't it?
So amplifying that.
Amplifying it, exactly. You're making it pronounced. That's all.
Okay, so because you're doing the multiplication, so that.
Multiply and add. Multiply and add. Right? Are we together, guys? It's just multiply and add. Multiply the value with the background and then add up the total.
The background is always 0 or 1.
In this particular case I took, in reality, it's not like that. In reality, for example, if it is a scene, it will be grayscale. No, but I'm deliberately taking a very simple example, 4. So obviously, the writing is 1 and the blank space is 0. Or you could see, the thing is, it's your choice, Bhavan. You decide, do you want to write with black ink on white paper or you want to write with white on black? Right? Pick your choice, doesn't matter. And then you can define a filter like that, based on that. Am I making sense?
Yeah, if we were to look at it from a computer terms, right? So it's basically the pixel with some kind of RGB number in it.
No RGB, no RGB. I'm just looking at plain grayscale at this.
Grayscale. Okay, got it. Okay. So, okay. Filled or not filled. Yeah.
Yeah. It is filled or it is not filled. Very simple, very clean shape of 4, written with a straight, good quality chalk, right, on a blackboard. So guys, are you understanding the concept of a filter? I notice we are pushing the time, so maybe we'll continue next time. But do you understand filters now?
So Asif, just one question. I think I've understood, even if I don't understand the math fully, but if I assume that it's a black box, there's a vertical edge detector, there's a horizontal edge detector, and so on. So what we do is we run these filters through the entire image, is it? And then we this is where we found vertical edges, this is where we found horizontal edges. Is that the sequence?
Yes, that's what you do. And I'll show you a simulation. It's a very good example. Each filter detects what it wants to detect, isn't it? the edge filter will come up with this bright yellow outline on the picture. Would you agree with that, Mahesh?
Correct.
If I take the filter and scan the entire picture from top to bottom, everywhere, it will end up drawing the edges.
Right? Understood. But just one slight clarification here. What we did was we took the image, we converted that into a one-dimensional vector. So inherently we lost.
No, we did not convert it to one-dimensional vector. No, we did not.
Okay. So this is a different.
That was the old way of doing it. That was when we were using it as a feed-forward network. Here we are not doing it. Guys, let us go over this territory all over again. Here is a picture, right? In this picture, there is a big fat 4. Do you notice that I'm not playing with the pixel? I'm not flattening it. I'm not doing anything. It is in grayscale. Let me leave the rules here. Actually, I should have used the white color just to emphasize that this is black and white. But anyway, I have. So let me write the rules here. This inside is +1. Outside is 0. Black is 0. 4 is written with a chalk, white chalk. Well, it happens to be pink here, but white chalk, and it is +1. So what it means is, suppose this picture is 100 by 100 pixels. Each pixel, each cell, so it is decomposed into 100 by 100, 10, right? 10,000 cells, 10,000 little pixels it is divided into. Each pixel can have what possible values? 0 or 1. Each, there are 10K pixels in this example, each having a value 0 or 1. As simple as that. I take a filter which is this filter, 8, -1, -1, -1, -1, -1, -1, -1. And I go like this. I start the filter here. First, place it here at the top left. Top left. When I place it at the top left, by the way, what will be the value here? Everything multiplied by 0 will give it a sum total value of 0. Right? I write it down on a table. I say my top left value is 0. Right? So this filter, now I slide it just one left. So it becomes this filter. This filter. Now what happens? Now something interesting is beginning to happen, right? At the bottom right, I noticed that there was my filter had a -1 and it gets multiplied with a 1 here. Look at the bottom right of this filter. Now it gets multiplied with a 1 because it's overlapping a 4. So my next value is -1. I feel good. I slide it a little bit more, and now my filter comes. Let me pick another color. What would be a good color? Green. My filter is this. Can you guys see the green filter now? This. What happens now? Let's look at this. We have two of them will overlap at the bottom 2. What are the values sitting there in the filter where it overlaps it for? -1, -1. They add up to?
-2.
-2. And this will continue here. And then you go further, you bring it. The third one, I can bring some other color here. After green, it is this. You realize that again, there's only one cell that is overlapping. Only this cell is overlapping now in the orange position of the filter. So this value will be back to -1, right? You probably saw something, but it's gone back to -1. Isn't it, guys? right? And you continue this filter. So what will you end up? This thing, it's a good point to mention. This is called a feature map. You are seeing this filter as this particular filter as it is sliding over the image. It is putting its values there. But now think, when this filter, right, slides, like it has been sliding here, it comes down. Let's say that when this filter becomes this filter, actually I need some colors here. Let me take this color, dark green, maybe. When it is sitting here, do you see where I'm moving my pen, guys? What happens at that moment? There is a big 8 that comes here, isn't it? And you will see a very pronounced value, positive value, somewhere here, wherever it is. Some positive value will show here. That will, so if the positive values are bright color, negative values are dark color. Actually, I put 0, but let's just say like that. Then what happens? What is it trying to say? I am sitting upon edge. Right? I'm sitting upon something. That's all it is. That's what you do with a filter. You go sliding all over the image. You keep sliding this, then here, then here, then here. All over the image you go. And then you start filling up a table. What is the net value you saw? That set of values is called the feature map. Are we together? Then you can take out another filter and another filter and do that. So let me show this with a real illustration. Let us go and see this in action. Today, by the way, we are not done with CNN, but we will. I invite you, I put this link on your course portal, guys. Right? Let us see how this works. There are these pictures. One is a something. The other is a ladybug, it seems. One is a pizza. Yeah. So let me take this. Now, this is a real picture. Are you guys seeing this picture, guys? Right? Maybe I'll increase the font size. 1 second. Yeah? Let's just look at this. This is a cup, a picture of a cup in 3 channels, like red, blue, green, because these days pictures are in RGB, multicolored. But for the time being, ignore the multicolored part of it. Just say 1 channel. Look at this, red. When you look at this picture, do you see that it has a lot of red in it? So the information in red channel will be pretty pronounced. Let's click on this. We are clicking on this red. Look at the convolution. We will click on this first filter, convolution filter. See what is happening. Do you see this little filter sliding over the image? You guys see where my mouse is, guys? What is it doing? It's sliding over the image and it's picking up the value. Literally multiplying the filter with the background. And as it is doing it, what is it ending up picking up? It is drawing the shape, isn't it? Right? Look at this. What is it doing? I can go over any pixel. See, I'm moving my mouse. Do you see where I'm moving my mouse, guys? There's a plus symbol here. Right? Look at this. This is dark. When this goes over it, do you see that the output is also background blackened? And what is the values here? The filters are, it's multiplying it with the filter. And at this particular moment where my value is, do you notice that, by the way, do you see, guys, do you see these boxes? These boxes are the background value. It's the actual value of the underlying picture's pixel value.
Feature map.
It's not a feature map. The photograph the image, its actual pixel value, guys, in the box. So we are covering only 9 pixels. That's a filter. Its receptive field is only 9 pixels. What is the filter's value? For whatever reason, the machine determined that the filter's value should be these. Right? And now this is reality. See, when I talked about edge filter, that, in reality, and this is where deep neural networks differs from traditional computer vision. What used to happen is people used to hand create filters, edge filter, line filter, etc. Today, the great contribution of deep neural networks is we ask it to go figure out its own filters, right? So it has figured out this filter for whatever reason. This is the filter it has figured out. Are you guys seeing it? Right. And so look at this. This picture is, do you notice that it's gray, like dark, very light? So when you multiply all of these numbers, what is the net number you come to at the bottom? Minus 0.08. Do you see that, guys? Right. Do you see the convolution take place? You're multiplying each of the filter pixel values, filter and the pixel values. Right? You're multiplying 0.35 with this. Let me put it here. Let me place it here. Oh, I wish I could just leave it here. Look at this, guys. I wish. Look here. These values add up to this value. Are you guys able to see where I'm clicking with my mouse? Right? It adds up to this. And what is it rendering in the output? This mask is creating a feature map. Output is this feature map here. Right? Sorry. When I'm here, look at this. Look at this grayscale picture and the output image. As I move the filter, it is putting some values there in the output. Do you see it do that?
Yeah.
And it is extracting one feature, its own perspective, its own window onto the reality. By moving the filter across, each filter sees its own special reality of the picture. Do we see that? Right. Likewise, now, then you add some bias term, it doesn't matter, and you're adding up all the 3 channel values. So look at this. What does the blue channel do? Blue channel says, I look for blue, only data only, but it's coming up. So do you notice that the picture that the blue one comes up with is not so pronounced? It's relatively, because this picture really has a lot of red in it. Can you tell that the blue picture is not so pronounced, guys? Is it obvious?
Yes.
Yes. Right. So this is it. Each filter, as it goes across the channel, it sees its own reality. Now, here comes that thing. You take the filter value. Now, this is something I'm going to tell you, that after the filtering, the next thing you do is you activate it. Why? We need non-linearity, right? We always activate after the linear transform. If we don't activate, what will happen? A linear transform plus a linear transform is just a linear transform. Right? The same argument holds. Why do we call it a linear transform? Filter is nothing but product adding up the products, isn't it? The convolution is adding up the products. Was it true? Right? In math, you call it a linear transform. You need to activate it. Yeah. So you apply a ReLU function. Do we remember the ReLU activation function? Now, what is the quality of ReLU? ReLU actually for computer vision turns out to be one of the, and it was literally discovered along in conjunction about the same time and found very effective. I think it was Geoffrey Hinton who discovered this too. He found that when you apply ReLU to it, all the negative values go away, right? So look at this. This image becomes, look at this. What did it do to the image? Everything that was dark has practically gotten masked out, right? Then look at this. You're looking at max of 007. So very, very light. Here, mask of negative number. You notice that where my mouse is? Look at the number. Minus, what is it? Minus 0.35. What will ReLU do?
Make it 0.
Make it 0. 0, 0. But here, outside, is some slightly positive value. So pretty much this mask turns out to be not terribly, this particular mask turns out to be not terribly useful. Now let's look at this filter, this particular filters and masks, sort of interchangeable. Now look at this. Do you see the scanning process, guys? Pay attention to how the filter is scanning all over the image. And it is literally rendering it. Right? Do you see the process? Should I repeat it again? Look at this. I'll repeat it again. Look at this. How it is scanning over the.
In fact, we are seeing the bias. Where's the weight?
Hmm?
Where's the weight?
The filter, the values sitting in the filter are the weights. So guys, it drew this, isn't it? And now it goes into the reloop. The next thing you do is the reloop.
In this case, each the links,
yeah,
the edges,
yeah,
or filters
mm-hmm.
with the different weights.
Has different weights. Yes,
yeah,
each filter is unique.
Yeah,
each filter is
each
unique.
edge is a each edge is a filter. In other words,
each
edge.
No. Each of these boxes that you guys are seeing here, this vertical column of boxes, each of these is a filter. Like, it's not the filter, it's the result of the filter. See, I'll go over this again, guys. I'll click on this. Do you see this kernel here, little?
Correct.
That is the filter.
That's a filter, right?
That tiny thing is the filter.
Okay, so the
that square
filter has the weights value.
Yes, that has the weights value, right? And look at this. You see this, right? Yeah. This filter is these values, this tiny below the box values. They, remember, look at it. They remain the same. Do you see that? The filter doesn't change as it scans, but the background changes. Yeah. And it keeps multiplying. That brings about a property of...
It's the same thing like the W multiplied by that A
yes.
plus B.
That is it. That is your W. Now, one of the beautiful things, the reason CNN, and I'll end it with today because next time we'll continue, the reason CNNs are very efficient. You realize that the same filter with this, its weights are frozen once it has learned. It is scanning all over the image. Doesn't matter where it is, right? And it is picking up features. So there is an inductive bias here. This machine can work if and only if the reality in one corner of the world and the other corner of the world, like the filter cannot be ineffective here and very effective here. The statistical properties of the image have to be such, or the data have to be such that filters are equally usable, right? And that is, in reality, that's true, right? Like you don't need a different pair of eyes to look left and a different pair of eyes to look right. Isn't it? So that leads to weight sharing. And that weight sharing brings about, reduces the number of parameters in a convolutional neural network by a huge amount compared to deep, like feed-forward networks where every neuron is connected to every other neuron in the next layer and has tons of weight. So imagine that you have one layer of 100 and another layer of 100 neurons. How many weights are there? 10,000 weights. You realize that, right? Whereas here I can get away with just maybe 10 filters, each of them 3 by 3. So then how many weights do I have? Just 90. Right? Compare 90 to 10,000. You see how efficient it is? But the underlying inductive bias is that the world is doesn't get weird the moment you turn your eyes in a different direction, isn't it? That's another inductive bias that these things have. So guys, I'll end today. This is the beginning of CNN. It's a new neural architecture. It's completely new to you. Like what I would suggest is the CNN explainer, I have put a link to it. Spend at least an hour playing with it, guys. Can you please do that? Yeah. Spend an hour seeing how the machine sees. And believe it, there's evidence that this is all inspired by biology, by studying neuroscience. It's not that different from how human eyes, the brain processes the images brought in by the human eye. There's a close parallel to it. Right? And if you look at this, one more thing, as you go layer after layer, do you notice that the machine is coming up with much more as you go layer after layer, weirdly enough, the picture doesn't necessarily get that. Something very interesting happens. Look at this picture. Well, it is not so obvious from this picture, but it is beginning to come up with pretty higher order representation of what it is seeing. In this picture, it is not totally obvious. Maybe they have more layers. How many layers do they have? Yeah, Chris Ola's link is there, which makes the thing much more clear. But anyway, just to finish this, guys, at the end of it, it is leaning towards saying, I'm looking at an espresso. Right? Would you see from the representation that it does look more like an espresso? What is the second most likely thing? It's an orange. Oh, it's slightly plausible, right? Who knows? The cup is orange.
The next one is bell pepper.
The next is bell pepper. And so, by the way, Chris Ola is one of the very deep thinkers in this space. He thinks really well. That's why I said it's a must-read article. Read this article, guys. Must read. Read it. Come. Now, some of the things that he may say, or he may use language which is meant for practitioners in the field, but actually he is as clear as it gets. Read it, and you will see. So anyway, I won't get into it, but in a way, if you want to see how the machine looks at the reality, look at this. Yeah. This is how machines dream of reality.
So Asif, it's also improving the image also. In a way, it is making it uniform, so it can identify it better.
Yeah, it's taking abstract representations from it, and we'll talk about that. Representation learning is a topic that CNNs are very good at, and we'll take it up the next time. How is that?
Okay,
so
CNN is playground is that you're showing? Is that a link in the portal, or you're showing that?
No,
just,
everything
separately?
is a link. So if you go to the CNN page, or if you see the page on convolutional networks, the section contains CNN explainer, Chris Ola's thing, the chapter, and all of this.
So Asif, all of the let's say face recognition in either Google Photos, Apple Photos, or any of those, all of the filters and masks in Adobe Photoshop and those things, it sounds like they're all built on top of these building blocks, right?
Yes and no. See, in the world of computer vision, the number of neural architectures that play, CNN is a dominant one, transformers are a dominant one, autoencoders play, variational autoencoders, GANs, diffusion models. Computer vision is a field that is rich and replete with different neural architectures. We'll meet many of them along the way. See, all of this magic that you see, Mahesh, like, these days you can take an image and tell Adobe, just change the guy's shirt color, right? And it does it. All of this is the end result of decades of thinking in mathematics. So it's beautiful, actually. But we use a lot of things there. You will learn, all I can say is by the time you're done, you would have learned something about all of them. But guys, you'll have to put in some effort, go and read up. Put some time and read up on it.
Asif, computer vision, so CNN is one of the computer vision family of computer vision, is it?
CNNs are dominantly used in computer vision. They are used for audio. See, where is CNN useful? In a way, any domain where these inductive biases are true. What were the inductive biases I talked about? You have some sort of translation equivariance. So for example, speech, human speech, right? Time series data. The local structure is there. There is hierarchical structure. Any kind of data that reflects these qualities or that benefits from these inductive biases, CNNs do very well.
Got it. Thank you.
All right, guys, with that, I will take questions.
One question, like in self-driving cars, do they use this kind of computer vision technology, or is it different to detect?
They used to. They used to.
Okay.
Now the world is more complicated.
As usual. Thank you.
But you learn all of that. You learn all of that gradually.
Thank you.
As if I was thinking about the use case of when they read poetry. So, which of these attributes come into play when they are trying to interpret poetry?
Poetry, you mean, but poetry is given to you as text.
Yeah.
If it is given to you as an input text, then generally CNNs are not the appropriate architecture. Transformers are a better suited architecture for that. But if the poetry is handwritten on a piece of paper and it has to figure it out, then CNNs are very competitive in figuring out what's written on that first. And then the interpretation can be given over to a different architecture, like an attention network transformer.
So, Asif, CNNs can be used only for vision.
No.
Only images.
No, I'll say that again. CNN is applicable to any data domain that shows these properties, these inductive biases: translation equivariance, local structure, locality, a hierarchical structure. So examples are images, sound, time series data, right? Thermal data. There are many, many data sets where these properties hold true. In fact, to some extent, text also can be processed, though in text domain now we have better architectures. Text also shows locality of reference, right? Local structure.
So how is it in the time series? So for example, let's say weather is a time series data.
Yes.
I'm getting like a temperature, wind, precipitation, a lot of other things. So how that can be used on the CNN domain?
Exactly like that. A time series data through a Fourier transform can be converted into an image.
Oh, okay. So the Bell spectrograph and then like
Exactly.
spectrograph.
Spectrograph. I see. Right? So we can do that. The moment you do a spectrogram of any time series, especially sound, in
So
sound
converting
case,
into an image and then like feed it into this.
Yeah, that's right. So it's all feature engineering. The moment you can make it in some form of a visual representation,
okay,
then it's a home run for CNN.
Got it. Okay. That makes sense. But same thing we did for like we do for the audio as well.
Yes. For example, if you want to distinguish, one of the success cases was, you probably know that, actually I'll stop the recording, otherwise people get bored listening to